Okay, so we're very happy to have Thomas Ferguson back to give part 2 of his talk on models of relevant arithmetic. Go ahead, Thomas.
Hi. Okay. Well, first, thank you all very much for having me again. So last time I talked about this topic, it was slightly more philosophical in nature. I was trying to motivate Bob Meyer's program of relevant arithmetic from the 70s and sort of examine its rise and fall. This I think is going to be a little bit more model theoretic in nature. I'm not so much interested in why one should embrace relevant arithmetic or something like this, that kind of question. I'm more interested in how do we look at the models and what can we get by applying standard model theoretic techniques to the models of relevant arithmetic. So I'm going to do a brief, again, sort of review of what R-sharp relevant Peano arithmetic is. I'm going to talk a little bit about some definitions for doing finitely valued model theory. So model theory for finitely valued or many valued logics with finitely many values. There's one particular thing that I'm going to discuss, which I think is a good application of model theory, which is this Meyer-Mortensen alien intruders theorem, which is a riff on a letter from Dedekind describing non-standard elements as alien intruders in the natural numbers that he's trying to find a way to eliminate. And I'm going to discuss some of the sort of not necessarily pathologies of their theorem, but some of the weird phenomena that occur. And then I want to talk about how using the technique of ultraproducts can serve to clarify some of the things that were mysterious in their result. So this is based on a paper I co-wrote with my student at UNAM, Alessangela Ramirez. And I really like the title, Episodes in Model Theoretic Xenology, because I get to use this line from Roadside Picnic, right? That xenology is an unnatural mixture of science fiction and formal logic. At its core is a flawed assumption that an alien race would be psychologically human. And part of the point of this paper was that there's something xenological going on when you're looking at these, alien intruders, that Meyer and Mortensen are trying to understand these objects as rational numbers, but looking at them as elements in an ultraproduct allows you to view them through their own sort of alien psychology and lets you understand them a little bit better. So, and again, also this is, much of this is a riff on the work of Bob Meyer, who had a relevant logician who spent most of his career in Australia and had forwarded this program of relevant arithmetic. So relevant arithmetic is analyzing the Peano axioms and the induction scheme based on the logic R. So R is a weaker logic than classical logic. We lose some theorems, and so typically we'll find that the theory itself is going to be like a sub-theory of classical logic. Notably, the conditional in relevant logic is intentional. It's not like the material conditional where A implies B is equivalent to not A or B. There has to be some kind of intentional connection. So you can look at this, where most of you are probably more familiar with thinking about like intuitionistic hiding arithmetic. And it's got an intentional conditional, right? Where A implies B is there exists a construction such that it turns constructions of A into proofs of B, right? It's got intentional flavor. It's not just reducible to negation and disjunction. So we take the standard axioms of Peano arithmetic. Induction, in Meyer's case, he treats it as a rule. Nothing really hinges on this. But we just close those axioms under this relevant logic R. And that gets us relevant arithmetic. So just some preliminaries. Again, since this is less philosophical and more model theoretic, a lot of this is taken from a paper I did on non-deterministic model theory, first order model theory. And non-deterministic logics are many valued logics, but the connectives assign values in a sort of non-deterministic way. And the notation that I'd used is what we have in the following, and I'll continue to use it. Right? We have a set of truth values. To get Woosh's theorem, we need to assume it's finite, but in general, that doesn't matter. And we have a set of designated values, which is a subset. And the easiest way to think about designated values is a generalization of the value of truth, right? So something's being true in a model is going to be identified with something's being assigned a designated value in that model. I mean, there's danger in making that equivalence, but for our purposes, it's fine to think of something as truth-like if it's a value that's designated. For each connective, right, enter a connective, we're going to have a truth function that assigns n tuples of truth values to truth values. And for every type 1 quantifier, there's going to be a truth function that maps collections of truth values to truth values, right? So you can think of, like your typical classical values over the or truth functions over the values of true and false as being, right, like conjunction is min, right, between two values, right? And you can think about quantifiers in this way, right? If we have the interpretation of the universal quantifiers, that's the minimum of any set of truth values, right? So that's how we can sort of interpret these in a very sort of general way. So if we have a signature and a set of truth values, then we're going to define a structure as a pair that has a domain and an interpretation. So it interprets constants. Those constants receive an interpretation in the model and the domain. For function symbols, right, it gives assignments to the function symbols, and there should be a superscript there, sorry. And importantly, for predicates, right, for n-ary predicates, we interpret these as functions from n tuples from the domain to truth values, right? So again, you can think about what does it mean to be, the interpretation of identity, right? And classically is, identity is a function, it's associated with a function that maps pairs to true if those elements are the same, and it maps pairs to false if they differ, right? So these are very sort of general definitions that we're comfortable with in the special cases. All right, so the valuation, a structure will induce a valuation, right? And I'm going to borrow sort of what I think Philip Rothmuller, that's my go-to book on model theory. I'm going to borrow his definition for quantification, where we think about an expansion of a structure where we have a name for every element in the domain. And so we can use this to give a full valuation to all the sentences in a language, right? So for atoms, right, we have a truth function for that relation, and the value assigned to that atom is whatever that truth function assigns to the denotations of those terms. For truth functional sentences, right, whose main operator is a connective, right, we do the same thing. We have a truth function, and it maps the values of the subformulas, right, to a truth value. And for quantifiers, right, we take the set of all essentially substitution instances, right, because we have a name for every domain. That gives us a set of truth values, and the interpretation of the quantifier maps that to a truth value. And also, by the way, just general open invitation, if I run too quickly past anything or something I've said is not clear, or just if something I've said is stupid, right, please feel free to jump in, interrupt me, and show me the light. Okay, so we have the turnstile relation. We identify with a sentence receiving a designated value by the valuation induced by a structure. So again, we don't need to be overly particular about the interpretation. So we're just going to say that phi is true in a model, right, or a turnstile phi, if that valuation maps a sentence to some value in the designated values, right, some truth-like value. Okay, so hopefully I didn't go through that too quickly. It shouldn't be I think, too foreign. I think they're very natural generalizations. Okay, so I want to focus on this alien intruders theorem, which was due to Meyer and Mortensen. It was only published in an ANU technical report. We republished it in the special issue of the Australasian Journal of Logic. So it's now available. You can go and get it for free. And it's got some interesting results in it concerning the models of R sharp. And one of the title itself, as I said, it takes its cue from this letter from Dedekind. He's thinking about how can we axiomatize, what kind of axioms do I need to add to secure and lock down the natural numbers as the only possible model, which again, this is Dedekind, we didn't know that it wasn't possible at this point, right? So he asked, what then must we add in order to cleanse our system of such alien intruders as disturb every vestige of order and restrict it to the natural numbers? So these alien intruders, just to, refer to these, we're used to them as these non-standard natural numbers that sort of hang out above omega. Okay,
Thomas,
the way that Meyer and Mortensen go about this.
Can I ask you?
Oh, please, yeah.
Quickly, do you know when Dedekind wrote that letter?
I actually, the letter, it's in a translation by Hao Wang. I could find that for you easily because I have a PDF of the Hao Wang. So it's in his 1975 axiomatization of arithmetic in the JSL is the translation of the letter. I'm sure it's in there. I can hunt it down.
No, don't look for it now. But it's known. I just wondered more or less what was the sort of time period, related to Cantor and other later developments.
Yeah, afterward, let me hunt down that PDF and I will let you know if I can. I'm pretty sure that it's documented in there.
All right.
Yeah, thank you. Okay, so the citing for Meyer and Mortensen's alien intruders theorem, which is essentially that the variety of alien intruders in relevant arithmetic, models of relevant arithmetic, is even more wild and wacky than you get in the classical case, right? So this is an example of looking at model theory for relevant logic as model theory, right? They're interested in the features that arise and they find these curious features. So they work in this logic they called 6, and it's got 6 values. Don't worry about us affording too much interpretive merit to it because it's just a tool, right? It's got these values I, minus f, minus t, t, f, and 0. They're linearly ordered in a Hasse diagram. Designated values are I, minus f, minus t, and t. So pictorially, right, we have these values, they form this lattice, and the designated values are all those things that are greater than and equal to t. And then the same remarks that we had before, right, get us, how do we build a structure? How does the structure induce evaluation of the language and so forth? So to interpret, right, connectives and quantifiers, because this thing has meets and joins, right, and infinitary meets and joins trivially because there's only 6 elements, right, we get definitions of conjunction and disjunction and universal and existential quantification for free, essentially, right? Because we can, well, what is the disjunction between 2 elements? Well, it's just the join between them, right? Yeah, so for the conditional, right, it has this relatively bizarre truth table for the conditional. Again, we don't need to afford any interpretive merit to it whatsoever, but we'll look at it again in just a moment. Okay, so how do they find a model and what are its properties? So they start by thinking about the integers mod n, right? And they call in the positive language of Peano arithmetic, right, we take the integers modulo n, and they observe that each of these, interpreted classically, is a model of Peano arithmetic in the positive language, right? So notably without the inexistence of predecessors to 0. And then they prove this model transformation theorem, and we'll run through some of the steps, right? So for any of these models, we can convert this into a model in this logic 6, such that all theorems of the relevant logic RQ are valid, that the class of valid sentences is closed under modus ponens, it's closed under the rules of relevant logic. Every sentence true in the integers mod n takes the value t in this model. And as I say, since a good guy by the lights of this model, every sentence false takes the value f in this new model. And also for any positive sentence, its negation, I'm sorry, there should have been a different symbol, but this negation is designated, right? So essentially, for all positive sentences, their negation is going to take a designated value. Not true, right? But it will be designated. So they give a little recipe for construction. I'm sorry, there should have been a bullet point there, but we just take as the domain of M6 sub n, the integers mod n. We interpret constants and functions and identity. We preserve these again. So we identify true and false T and F from that lattice with true and false classically. So that gets us the initial valuation of literals of atoms. And then we just extend the valuation per those definitions of 6 that we saw that were induced by this and this truth table, right? So we have essentially the diagram of the model. We inherit it from the integers mod n in the positive language, and then we can start evaluating it in the full language of relevant arithmetic. Okay, so they gave 5 points. Most of these are very, very, very trivial. This is a so-called De Morgan monoid, that lattice that we saw, and it's known that that models relevance logic. So we get 1 and 2 essentially for free based on the structure of those truth values. So it's a model of RQ, and it's closed under the rules of RQ. Points 3 and 4. Every sentence true in the integers mod 2 takes the value T in the M6 sub n, and it's good guy. The proof is pretty much simple, right? The base language is negation free. All atoms agree between these two structures, and conjunction, disjunction, and quantifiers restricted to the values T and F agree with their classical counterparts, right? So, right, you see like that if I only have inputs T and F, right, the meet and the join between them is closed, right, under T and F. So that diagram, the positive diagram is going to be preserved in a sense. Again, equating truth with T and falsity with F. And this holds also for that interpretation of the conditional, right? So if my conditional truth function takes values F or T, right, as inputs, it's going to output a so-called classical value as well. And for point 5, any positive sentence, not A, is designated in that new model. It maps any positive sentence to either T or F, right, by hypothesis we just saw. And so its negation is going to be either not T or not F. And if we go back to the diagram, not T and not F are both in that filter. They're both in the set of designated values. So all negations of positive sentences in a sense are true. Again, in scare quotes, right? They're true in the model in some sense. They take designated values. So also you can go on and you can prove that each of these interpretations of the integers mod n is a model of full relevant arithmetic. So I'm going to admit it, but it follows from a pretty straightforward induction on the complexity of sentences or formulas. Okay, so this alien intruders theorem, right, which is sort of the centerpiece of this technical report they wrote, it describes that we can get a weird model that's a model of relevant arithmetic, and it has some interesting features, right? It has alien intruders in it, but those alien intruders are rational numbers in a sense, right? You can take them, you can construe them as rational numbers. So we're used to these Dedekind's alien intruders as, you know, these things that are living in this data times eta block that lives way above omega. But there's a sense in which the alien intruders form a broader class in relevant arithmetic, because now rationals, the entire rational numbers, those are also serving as integers or as natural numbers in some sense by the lights of relevant arithmetic in these models. The ordinary laws of rational arithmetic hold: addition, multiplication, subtraction, division, and the Peano postulates are satisfied by this model, including mathematical induction, right? So yeah, so I'm not going to go into the proof of it. What they take from this, well, I'll read you the line from the technical report, which is sort of their takeaway from discovering this model is all of this is, to say the least, most startling and wonderful. Bereft of the paradoxical properties of classical negation, it's possible to satisfy the Peano postulates in a domain that contains all the rationals among the alien intruders. So they find this to be, look, intriguing from with the model theorist hat on. Like there's this, interesting structure that occurs, and it's got more structure and texture than the classical case. So it's something that's just interesting from a mathematical perspective. The proof technique, though, leaves something to be desired. So I'm not going to go through it, but the technique is important to mention. So the technique follows from adding a new constant for a new natural number, so n to the signature, interpreting the equivalence as equivalence mod n, which is definable in the language, of course, and adding an axiom that every x is either equivalent mod this new n to 0, or there is something that multiplied by it is equivalent mod n to 1. And we also add this axiom, it's not the case that m is equal to n for each numeral, right? So 0, successor of 0, successor of 0, and so forth. So they show that every finite subset of this set of sentences has a model in one of these M6 sub i's, right? So every finite subset of these sentences has a model. And so by compactness, the entire set of sentences has a model. But this model, of course, has this new constant that is not identified with any of the m's, right? And therefore, you have to have a model that has some non-standard n. And then they go through this model, or anything that would follow from the compactness theorem, and show that it would have these properties so that it would have all the rationals in it.
Can I ask something here?
Yeah.
This is just my ignorance about non-classical logics, but there's a compactness theorem for relevance logic. What is it? Is it sort of more or less the same kind of sort of a translation of what's done classically, or
yeah? So if there is a model, right? Again, something is models of a sentence if it takes a designated value in the evaluation that's induced by that structure.
Right.
So if every finite set of sentences has a model, then the entire set of sentences has a model. So it's the straightforward, same. It's a compactness theorem, and I'm trying to find cases in which compactness doesn't hold, but certainly it holds of R, and it holds of the extensions of R, of RQ, of quantified relevance logic. And I can't imagine any counterexamples unless we think about like second order R.
Oh, I see. So just to follow up on Thomas, just to follow up on that. So, but at the beginning, you gave this very general version of what those logics could be, with designated value and the arbitrary sets of truth values and all of that. So is it known that some assumptions about that are needed for compactness, or?
I would imagine, and I would imagine, and I can see how you would prove this by like kind of a Lindstrom type technique, that any structure that oh wait, I'm sorry, yes, it holds. It's a consequence of Wusch's theorem. Oh yeah, of course. Any model that I just described, any logic that has the semantics that I just described, compactness is gonna hold because of Wusch's theorem. Because that's our first like hand-holding introduction to the power of ultraproducts, right? Is you can get compactness. So yeah, it holds if anything that receives the semantics of the type that I described in the first 5 minutes.
Oh, that's interesting. It's very interesting.
So it's more or less like a similar compactness type argument.
Yes.
Sorry, ultraproduct argument.
Yeah, and I'll define those in the general case in just a moment. But yeah, I'm sorry. So compactness is it holds in this case. It holds certainly of the logic 6, and so they make a compactness argument. But the important thing about this is the pulling a rabbit out of the hat feel that you get for inferring the existence of a model by appeal to compactness, right? And that's what this paper intends to sort of clear up, is that we don't need to have a magic act, right, to see why some of the phenomena they're on the screen right now hold in the model. We can dig deeper because ultraproducts afford more clarity into the structure of the models. They're not constructive, right, because they, non-principal ultrafilters and so forth, but they are less opaque. They expose some of the machinery, and that, I think, I'll show you a few cases of how I think that clarifies some of the things. So yeah, compactness we get, and we'll actually, as a corollary, we'll essentially prove it in like 5 minutes. And the critique I have of the argument in the paper is that the proof by compactness is not revelatory in any sense. It doesn't provide any clarity. So, and it doesn't provide any clarity to the phenomena that you have on your screen, right? So it strikes them as implausible or just surprising. They don't mean it pejoratively. It's surprising and magical that we should have a model of arithmetic in which all rationals sort of operate as though they were natural numbers. It seems weird that induction should hold of these rationals, but I will point to, again, the later result that we talked about last time I was here, the Friedman result, right, showed that, gave a very clear argument for why induction holds over the complex numbers from definability, right? But this is 20 years prior to the Friedman result. So it's still
Thomas, another question. Sorry, maybe we should raise our hands to not think. But when you say, well, it's somewhat paradoxical that induction holds for the rationals, does it mean that the rationals are definable in the model? So it's a definable subset, so then an induction applies to it? Or that would be paradoxical.
That induction should continue to hold over this domain.
Right, but the rationals are really alien creatures, and they don't really live in it in any kind of arithmetic way to which induction applies, I presume.
Well, but again, from the perspective of the model, they're indistinguishable from natural numbers, right? So,
but in what sense?
Are
other elements distinguishable?
No. I mean, it thinks it's a model of arithmetic, right?
Right.
And,
but does the model know anything about who's rational and who's not?
That's an interesting question. Yes, you could probably write formulas that would. I don't. It's a weird thing. I don't have ready, like, in my pocket, a really fantastic response to that, because I don't think it's been really explored about definability in these kinds of models. I just mean that it's surprising. Mathematical induction seems to really stand or fall with the discrete structure of natural numbers, right? And there's a sense in which, as soon as you look at non-standard models, it's not so surprising, I guess, right? Because you have these weird creatures for which mathematical induction holds, but that's still kind of mysterious, right? Because you start off with 0, and then for every number you go to its successor. You think about something like, why should the fact that the induction hypothesis holds, and that it holds of 0, why should this cover 3/4? Right? Doesn't mathematical induction like skip over 3/4? Like, why should we be able to?
So that would be really a good topic. If this was a philosophy seminar, we could continue forever. I think this is interesting, how to go from it. But no, I don't remember. But I think I do know, and you did tell us last time that the complexes are a model of right. So we know, so rational numbers certainly live in the complexes, and induction applies. But the complex numbers know nothing about rationality. This is everything's highly undefinable, and that's why induction holds there. Because it's easy for induction to hold because there are so few definable properties.
I have a question that goes the other way around. Although I don't know anything about this underlying logic, but what about Julia Robinson's theorem about defining the integers within the rationals? sort of turning.
No, that's right. That's exactly the point. So no, but this is the power of the rationals as they, as they are, right? So and it takes a lot of, a little bit.
Maybe the issue is the quantifier complexity of that, and it's not compatible with what's being.
Right. So it holds in the domain of the rationals, but in these strange creatures, rationals just live there as some kind of a scattered set that the model really doesn't know about.
Yeah. I'll tell you what, how about, so we're going to actually look at in the ultra product why there are rationals, right? So I think these are really, really, really good questions, and I'm going to be kept up at night for a couple of weeks over it probably. But like when we actually look at an instance of a rational in a model of relevant arithmetic, maybe that will give us a little bit more of the tools we need to have this conversation. Would that be okay? I'm going to go on then, and let's pick this up in maybe 10 minutes. I think we'll have a little bit more insight into the structure, and we can maybe jam about this with a little bit more precision. Because look, right now, a rational in this context it's still vague, right? Like this is hinging on the fact that I'm using the word rational in this sort of gesturing way. Like it has some properties, but we'll look at it in like 10 minutes. Okay, so the last thing that is of these that I selected to kind of look at is some weird things like the predecessor to 0. There's a predecessor to 0 in these models. We can call it -1, and this receives a 4-square expansion because Lagrange's theorem for square theorem, right, holds because it's a model of relevant arithmetic. So every number has a 4-square expansion. But it seems kind of weird to say that this negative number has a 4-square expansion. There's something kind of weird about that. So with the level of expressivity, the tools that they have, these things look very, very mysterious. But what I want to show, right, is that looking at similar constructions with ultra products shows us why these things aren't so bizarre after all. So so unfortunately, the Meyer-Mortensen proof follows from compactness. So we don't know anything about the inner structure of this model. We just know that its existence is guaranteed, right? And we're not going to know everything about the inner structure of the model when we have an ultra product, but we're going to be able to look at it in a more refined fashion. Okay, so I'll define ultra products. Again, this is relying on the definitions that I gave earlier. We can think about a product of these structures, and in a relatively more or less standard way. We can think about the interpretation of a constant in the product of a family of structures as being the product of all of the interpretations for the individual structures itself, right? And the function, right? Functions we can interpret in a similar way. So making sense of the interpretations of constants and functions in a product structure makes sense. Now, here's something that the many-valued case differs quite a bit with the classical case. So in the classical case, we have a very nice way of interpreting relations, n-area relations, but we get stuck at the point of thinking about a product of structures in the general many-valued case, right? So in the classical case, we can assign a truth function, right, from n tuples from the domain to true and false with the following scheme, right? So how do we interpret a relation? Well, it assigns the sentence true if for every interpretation, the local interpretation of that individual model indexed by I is true, and we're going to call it false otherwise. All right, so that's, the standard thing, that we get. That's how we infer that the product of structures is itself a model in classical logic. But we get this because we're identifying false with not t. It's our only alternative, right? So we can just say otherwise everything is false. But when we have more values, not t, the value other than t, does not uniquely pick out a competitor, right? So we don't have this nice way of defining an interpretation of relation symbols in the many-valued case for a product. So we lose a guarantee that the product structure will be a model in a sense. It's not going to induce a relation necessarily. It's a well-defined structure, but it's not going to be able to support an interpretation of the entire language in general. So we do win this back in the case of the ultraproduct. So we do have a guarantee that ultraproducts are in fact models for any of these, semantics that we've looked at. Ultraproducts, right? So if we have a family of many valued structures, and we have a sentence phi and we have a truth value, let's say math like frac v, we're going to use the following notation. We're going to say that phi in the brackets with a fractor v is all of those indices at which the model indexed by I assigns that sentence that value of v, right? And we'll just drop the notation, so drop the subscript, so that we'll just say that the brackets of phi, this is all of the indices at models in which it's designated locally, right? So pretty standard generalization of the notation that you usually encounter in these cases. We have, so if we have the this index, we can, and it's infinite, we can define an ultraproduct on its power set. And we can, this induces an equivalence relation. And, so A and B, elements A and B from the product structure are equivalent if those two elements are identified at almost all indices, right? So almost all of the individual local models identify these elements. So we say that they're equivalent modulo that ultrafilter. And we'll just say that A with a subscript here is the equivalence class of all elements of the product that are equivalent by the lights of the ultrafilter, right? So this gives us a domain, right? The equivalence class for the ultraproduct is going to be the domain of all the collection of all those equivalence classes, right? And then the rest of the stuff is very straightforward. Like, how do we interpret a constant? Well, the constant is the equivalence class of all those elements in the product that are identical to its interpretation in the product. And the same thing applies in the case of functions, right? So those, again, this is inherited from the classical case. Now, the nice thing is that, the worry before, why it's in red, is that we're not guaranteed a unique sort of interpretation to in the product structure for relations, but in the ultraproduct, we can give a nice interpretation, right? So we're going to interpret relations in the ultraproduct as assigning, as mapping tuples in the ultraproduct to the unique truth value, such that the set of indices at which the interpretation of that sentence receives the truth value v is in the ultrafilter. So what is the value assigned to an atom? Well, it's the value that almost all models in that family assign that value v to. And so here's where using finitely many values comes in, right? Because we have finitely many values, right? These sets right here, the sets, of indices taking each value, those are finite in number, right? They're also disjoint. So we're guaranteed that one and precisely one of those makes its way into the ultrafilter, right? If two did, then their intersection, since it's disjoint, would have to be an ultrafilter, so it wouldn't be an ultrafilter. And we're guaranteed that one exists because at least one of them has to be infinite, and either it or its complement would be in the ultrafilter. So we know that there is a unique value such that almost all models or structures in the family assigns that value to the sentence, right? So that's how we get the interpretation of the relation symbols, right? So unlike products,
sorry, again, some uninformed question. So then you need to have negations of some sort, right? Because if you know that one is infinite, and so one of them has to be an ultrafilter, but then it corresponds to some kind of a negation of a property that you assign. And so those truth values, they seem to be coming in pairs.
So we need negation in the meta language because we need to be able to talk about the complement.
Right, but then we need to know the right, and negation of each value is which value, right? Oh, I see. So it is in the truth value table.
Yeah, so that will just be inferred from the
Right. Okay.
atom.
Okay.
So in the same way that we showed how we sort of recursively build up that valuation. So
Right.
with diagram,
Mhm.
that gives us everything, right? So
Right. So in other words, it wouldn't be enough to have some kind of a total truth value and then to chop it into little pieces, and they say, oh, everything has one of those, but they have to come in those. So there has to be some duality between them. Okay, because there is negation. Okay.
yeah, but the negation is, I mean, you don't. It's different from classical negation because it
Right.
doesn't.
No, I understand.
Yeah. Okay. Oh, well, this is what I said, right? There's finitely many pairwise disjoint sets for this. Maximality, at least at most one must be a member of U of the ultrafilter, and the finite intersection property, only one could be a member. So this in particular, this schema here that this maps tuples to the unique value. This is well defined. Okay, so Woosh's theorem, right? I'm not gonna prove it. I have this paper on non-deterministic quantification where this is proven, and it's actually proven more broadly. It's proven not just for deterministic, but also non-deterministic logics. So if something has a finitely many values and its truth values, and the quantifiers we can express in a first order language. So essentially you can embed its model theory into ZF. Then we get this very specific version of Woosh's theorem that the valuation induced by the ultraproduct structure will assign every sentence V precisely when this set of indices is a member of the ultrafilter, right? And as a corollary, oh, the general version missed, it disappeared. Okay, as a corollary, we have a general one, right? Which is that phi takes a designated value in the structure if and only if the set of values of which it takes indices of which it takes a designated value is in the ultrafilter, right? So this is a very specific, refined version of Woosh, and we can give you something very similar. I just don't know where my slide went during compilation, but that resembles even more closely how you typically see the fundamental theorem of ultraproducts, right? So I'm not gonna prove it, but it's anything of the way of anything in the semantic approach that we just described has many values and has quantifiers again that we can describe first order. Woosh's theorem holds of it, and you're turning to the question of compactness. As a consequence, compactness holds of any of those logics as well. Okay, going on to look at applying ultraproducts to these models of relevant arithmetic. So the slide we had before, we saw this logic RM3. So instead of working at the 6-valued logic, we're going to worry about this. We've again got this lattice structure, T, B, and F as our 3 truth values. We've got a negation, disjunction, just join on that, conjunction, just meet. And again, because these things are linearly ordered and finite, we can interpret the quantifiers in a standard way as well. The only thing that's unusual is this interpretation of the conditional, but nothing's going to standard fall with it. So RM3 is a 3-valued logic. Importantly, it is intermediate between R and classical logic. So this is used by relevant logicians working in relevant arithmetic. It was used by Meyer and Mortensen frequently because if something has a model in RM3, so if arithmetic has a model in RM3, then it has a model in R sharp, right? Because RM3 is an extension of R. But we're going to use it because it's very well behaved in terms of models. So we're going to essentially run through similar steps that Meyer and Mortensen used and define ultraproduct that gives us is a little bit more revelatory, right? So gonna again take the integers modulo I as our domain for each of these a sub I models. We're going to interpret functions and constants as usual, and we're going to interpret identity the only relation we have in the following way, right? It's going to assign sentences to the value of b if the interpretation of those two terms is in fact they coincide in the model, and it's going to map it to f otherwise, right? So this is enough. This defines a model in RM3. And these, again, just to illustrate, these are the kinds of structures that we look at. We've got 0, also 1, 2, 3. All the numerals are equated with one object, right? 0, 1, 2, 3. We have 3 elements. And each of these is going to, induce a well-defined structure in the sense that we need it to. Okay, so theorem, we talked about this last time I was here. I think we went through most of the steps of proving it. I'm not going to do it again, but each of these models is a model of R sharp, of relevant Peano arithmetic. As a corollary, because we just showed Woosh's theorem holds for any ultrafilter on the power set of omega, this ultraproduct is also going to be a model of R sharp. So it works to deal with the ultraproducts. They get us all the right truths that we need to think about relevant arithmetic. Okay, so now we can think about rationals, and maybe this will provide us a little bit more detail in terms of to pin down the definition of rational a little bit more precisely. So we're going to identify an element in one of the domains of these local models, A sub I, with a rational A over B, if D times B is equal to A is true in that model. It takes a designated value in that model, right? So as an illustration of what numbers act as rationals are rationals in the finite models, right? We can think about the rational 3 over 4, right? And I've highlighted the element in that local model of relevant arithmetic in which the 3/4 would be identified with, right? So yeah, I'm sorry. I guess I'm not. I worked it out. I can't work it on the fly, but 2, right, is an element that 2 times 4 is equal to 3 in the integers mod 5. I believe that's the case. I used a modular arithmetic calculator. But yeah, so you can see what the elements think that they're rationals in some sense because they have the right divisibility properties. So we're kind of getting on to what is it like something resembling definability here. So it's not definability in the same sense, but we're circling around that, I think. So we can say, look, let's let this set denote the set of indices. So there exists there exists something that's A over B. So the rational A over B exists if there exists something times B is equal to A. So I'm going to describe some lemmas. I'm not going to prove them, but they're pretty straightforward. For all natural numbers, AB, the set, and also, I'm sorry, without loss of generality, I'm only thinking of positive rationals right now because we can fix everything up, but it's simpler for expository purposes. But for all natural numbers, A over B, the set, there exists some rational A over B is infinite, right? Because we can just keep on crawling up. And for 1, if we go back to this model, the index 1 or 0, the first model is always, every rational exists in this model because there's only one element, right? And then for this, we can crawl up. So for every A sub I in which there exists the rational A over B, we can find a larger model at which there exists an A over B is true as well. So each of these is infinite because we can just crawl up omega. For any, I'm sorry, this didn't compile right, but for any natural numbers A, B, C, D, this didn't compile right, but the set there exists an A over B intersected with there exists a set C over D. This is infinite as well, right? So it's the collection of all sets of indices at which such and such a rational exists. or for any rational existence, it's closed under intersection as well. And so as a corollary, I don't know, maybe I misspelled frac. I'm sorry, I don't know why this didn't take. But the set of all the finite intersections of the existence of any finite collection of rationals. This thing can be extended to a non-principal ultrafilter. We'll call it Q star. Yeah, so the notation didn't take. But what this is that for any, the collection of all indices at which such and such a rational exists, yeah, so this, I'm sorry, yeah, so I'm tripping over my tongue right now. This set can be extended to a non-principal ultrafilter, and in this ultraproduct, the product of all of these finite models of relevant arithmetic reduced modulo that ultrafilter, this includes all rationals, right? Because we're like, well, does A over B exist? We pick one. Well, the set of indices at which it exists, this is a member of this set, and therefore it's a member of the ultrafilter, and therefore that rational exists in this model. So we've selected the ultrafilter in such a way as to guarantee that no matter what rational you pick, that there's almost all models in there say, oh yeah, that rational exists here. Okay, so what can we do then to, okay, so the mystery in some sense of all wire rationals in this model, we can look at it in a relatively like a refined way using ultraproducts. What does it mean for all rationals to exist? And like, well, okay, what is it? There's infinite sequences or equivalence classes of infinite sequences over these finite models, and each of them thinks I am a rational at almost all indices, right? So we have a little bit more clarity into what rational means in this context, and I think that it serves to sort of clarify one of the mysteries of that Meyer-Mortensen attributed to their model. And we get the resolution of that mystery because we have a more revelatory technique. We have a more a model that exposes more of its machinery. Okay, so the mystery of induction, right? So Meyer-Mortensen say it seems magical that induction should hold the rationals, right? The reason they give, again, is more philosophical, but and again, very much prior to that Friedman result, is that, look, if we're thinking about induction, like thinking about 3/4, it seems to be a blind spot, right? In a sense, in induction, right? Induction starts with 0, and this is, well, if 0, it holds of 0, it goes to 1, and if it holds of 1, it goes to 2. Like, it never takes 3/4 into account on its face, right? So it's kind of odd that because the induction schema never takes 3/4 into account, that it should infer that this property holds of 3/4 as well, right? So we have an external explanation in some sense, right? Because, you know, like, we're already used to this in the case of non-standard numbers. Induction holds of non-standard models of Peano arithmetic. And so these models that Meyer and Mortensen have built, it's a quotient of a non-standard element. So that goes some way sort of externally to explaining why induction holds and why it should hold and why you should be able to infer something about 3/4. But we also get the sort of internal explanation of induction, right? Because the elements of the ultraproduct are essentially constituted by natural numbers, right? So what does induction really look like? It's as if B holds of the equivalence class of the tuple 0, 0, 0, 0, 0, and if it holds of the tuple MMMM, then it holds of M prime, M prime, M prime, the successor.
Thomas, can I say something quickly? Because Attar said at the beginning that today we have to finish a little earlier, and we're coming close to the deadline here. So perhaps you can say some kind of a concluding remarks, and then maybe we can have a minute or two for a discussion, because there is much here that we can talk about.
Okay, so the last thing I'll say, and then I'll conclude, is the same thing holds for four-square expansions, right? When we look at the fine structure of what the elements of the ultraproduct are, right, we've got a -1, right? But we can also say that, look, because of each of those elements receives a four-square expansion at the local model, it makes sense that we should have a four-square expansion to the predecessor of 0 as well. Because we can decompose each of those individual elements. So what have we seen? The technique is sort of magical. It appeals to compactness. We get a little bit more revelation if we start using techniques from model theory. And so applications of model theory are able to afford additional insight into models of R# beyond that achieved by Meyer and Mortensen. And that's the very condensed, truncated version of the last things we're going to say. Yeah. So you can imagine how you could see a four-square expansion holding in the case of -1. So I don't need to necessarily belabor it, but because of the structure of those elements, we can see why it would hold. That was the last point. Okay. Yeah. Sorry for running so close to time, and thank you very much. And any questions you got, happy to answer.
Okay, thank you. Let's all thank Thomas again. We can, if you'd like to unmute and clap, you can, or you can just use their emojis as we have been doing. We do have a few minutes for questions, and so I'll say this. I'll also when I need to go, I will just stop the recording and I'll leave, but I'll keep the meeting open in case there's more discussion for those who want to continue. So for those who are available. So I'll stick around for at least 5 minutes for the questions. So it looks like Jacob has his hand raised. So Jacob, you can go ahead.
Yeah, I was curious about the order type of these rationals, because you kind of put in quotations. It should be like what we would expect in normal non-standard models of Peano arithmetic, but is that true, or is that an open question?
So and look, so when I first started doing this, I have a Notre Dame Journal of Formal Logic paper on model theory for logics in this class. Actually, it holds of RM3. It thinks about models of arithmetic of a related sort. And I did consider the order type of these, and but the notion of order at this point doesn't make a lot of sense, right? You need to have, I think, a better notion of order, because if you go back to these cycles, right, everything is greater than everything else, right? And if you take a quotient of a non-standard model of arithmetic modulo, non-standard model of arithmetic modulo non-standard n, right? Again, everything's going to be in a huge loop and everything's going to be ordered. So it was a little bit mysterious, like, how do you talk about the order type of these things? Because everything is in some sense bigger, and everything both precedes and succeeds everything else. So I don't know about how to define order in such a case, but certainly I suspect that there's ways to talk about it, but I don't have the vocabulary really to express it, other than to say it's more complicated, or at least requires something more than talking about order type in the general case.
Thank you.
Did I speak past your question, or did I address it?
No, you addressed it exactly. Thank you.
You could think of
that
like,
holding. If anybody knows of a good way to talk about order types of things that are cyclical, I would love to have a reference, because I have wondered about this since 2012. So anybody have any suggestions about like order theory for things that are cyclical? Like, I want to know about it. But yeah, thank you for the question. It's a good point.
you could think of it as just being a finite chain with a top element, right? And so the ordering between two numbers would be based on their mod n comparison. So like 8 is less than 6 mod 7, because 8 would be equivalent to 1. Right? And
but then I think that there are problems here.
There'll be problems.
My biggest complaint about that, because this is not really the ordering compatible with the arithmetic structure.
No.
So things get violated. So these structures essentially are unordered. And so, because I was thinking about this, about one thing I want to say that, Thomas, I like the talk very much, and there are all kinds of interesting technical things to look at. But all those claims that somehow this is all Peano arithmetic is a little bit, I would say, misguided. This might be a wrong term, but I always thought that basic intuition behind the natural numbers is not the induction schema, but the well ordering, the fact that every set of natural numbers has a least element, and which is definitely not true here, right? That this is not really that because there is no ordering. So certain basic intuition about numbers completely is thrown out of the window to begin with. So there has to be some kind of a discussion of it, and but the lack of ordering is an interesting aspect. But this, because I might have mentioned it to you, there are these, though, like Boris Zilber was saying that this whole concept of number systems culminating with real numbers at the end, where everything's ordered and there's kind of a limit process of you complete the rational line with adding points. This is all fine, but the fact that number theory is so useful in certain areas of physics comes from the fact that the basic structure is the complexes. That it's not like you approximate this idealized number system, but by first going to a real line and then completing it algebraically, but to do the whole ultraproduct construction starting from finite fields. And so the ordering doesn't really matter that much. This is all in the world of science fiction a little bit, but there are some very interesting insights there that, from the point of view of foundations, those finite fields mean a lot. And then the fact that for forming an ultraproduct, you go immediately to the complexes. It's an interesting observation. And that's sort of about the nature of numbers. The reals, reals are very uncategorical. This is the question that, you have this kind of real and that kind of reals, and, and what about continuum hypothesis and all kinds of things like that. The set theory enters very strongly, but this doesn't happen with the complexes in a sense. Well, it does in certain sense, but it's anyway. But again, it's a longer discussion. I don't want to open, but I just wanted to sort of complain about the lack of ordering and the fact that there is no least number principle. That's bad.
Yeah, and look, I mean, one of the ways to think about something like Meyer's project is in that the catastrophic case, right? Like if Edward Nelson was right, and we need to whittle things back down. I mean, well, if like the catastrophic case where Robinson arithmetic is inconsistent, like what do we do, right? That, well, okay, Meyer's got this backup. In some sense, right, like I think what you're saying is that you've given up the wrong things. If you have to give up, right, the natural numbers as being, well ordered and going upward and not going back and folding back on themselves, then you've lost something critical, and it's not even an alternative worth taking. Yeah, I think that's a good point. But I guess there's sort of a idea about the role of negation here, is that negation doesn't serve to sort of rule out in the language itself. It doesn't rule out possibilities.